think I only missed 2 videos all year, so that's not bad. One was in my graduate course, though. It was a great lecture. I really hated it. But anyway, okay, so we're on our last few days here together. And so today I'm going to finish up the review for the chapters, and then I have an in-class exercise on synthesis. So our synthesis exercise is going to be with looking at the reactions forwards and backwards. 2 of them are retrosynthetic, or actually 3 of them are retrosynthetic, but then some of them are just fill in the blanks, fill in the reagent. So we'll sit there and think about that. So for the review here, we're up to chapter 10, which is radicals. And radicals only do 2 things. Anybody? Abstract a hydrogen and add to a double bond leading to another radical. There's only 3 steps to the mechanism. Initiation, where you have 0 radicals, and now you have radicals. Propagation, where you have radicals and you still have radicals. And termination, where you have radicals and you don't have radicals. So look at it that way. And remember that they have different reactivities and such. The benzylic and allylics are more reactive right there. And we can specifically do chemistry at that allylic and benzylic position using different reagents. But in the case of chlorine and bromine, remember that chlorine is more reactive and less selective. Bromine is less reactive and more selective. Okay, so we want to make sure we know our selectivity there. And we can add HBr across a double bond anti-Markovnikov. So the bromine is on the least substituted side. Technically, it does follow Markovnikov's rules, but if you want to remember it as anti-Markovnikov, that is fine. Okay. Now, again, methyls are least stable, but they're not so unstable we can't form them. We can form methyl radicals. Okay, even in the example right here, we're forming methyl radicals. The difference is not so great we can't form them. It's just that they're less stable than the benzylic and the allylic. Okay. So because of that benzylic position, if you have a hydrogen here on this benzylic position, and that's this right here, if you have a hydrogen here and you have bromine, you can brominate selectively right next to that benzene ring. Okay. And likewise, if you have a double bond and you use NBS and a peroxide, you can get allylic substitution. It's substituting next to the double bond. So it changed it up a little bit. It formed that allylic cation by hydrogen abstraction, but now that allylic radical is the one that's reacting, and you keep your double bond. So that's a really cool one to do. And then, of course, when we have our allylic right here, we have the choice that the allylic radical is going to spend some of its time here, and it's going to spend some of its time there. So you're going to get both products. But notice in the ring system, it doesn't matter which side it goes on, the double bond's still going to be right next to it. So it's really better for those ring type reactions. Okay. So in the case of just hydrogen abstraction, it's easier to abstract a tertiary hydrogen. So when you have reactions with bromine, you're going to get mostly this tertiary hydrogen abstraction and only some of the primary. In chlorine, it actually, the difference is not as good. It's only 4 times different. So you're going to get a 4-to-1 ratio. So it's a little bit messier, but it's still possible. And then our allylics can be very nice because if we do it with just bromine, we're going to get dibromination, allylic bromination, and we're going to get monobromination. So it's going to be just a whole mess. But let's be specific about our reagent, and we can get to that here. And of course, if we do it in the dark, we will just get dibromination. And notice this is anti-addition. Okay, so we can get one product from one reagent, one product from another reagent, and actually those plus several others in this, if we just did it that way. And then, of course, we have the Markovnikovs versus the anti-Markovnikovs. And notice this has an opportunity to rearrange and give us a tertiary carbocation because it's in the mechanism. This does not rearrange. This does not rearrange. So we have our anti-Markovnikovs addition, our hydrogen gets added here, and then our bromine, I'm sorry, here, and then our bromine adds on the end. So our hydrogen adds only on that position. So that makes it really, really nice and selective. Okay. So now we have a summary of a lot of reactions right here. And the reason I put this up here is not to go over all these reactions again, but to get you to think of the idea that it doesn't matter what the starting material is. You just need to know how it reacts and figure out what the product is from there. So right here, this is like the same as hydration, but we use an alcohol instead. Alcohol, we get an ether here instead. So we can make all these different functional groups from that same starting material. Okay. Now we're going to go all the way back to chapter 6 and look at that table at the end of chapter 6 for nucleophilic substitution. And there's 10 different things you can make. 10 different functional groups that you can have just with an SN2 reaction alone. So that's kind of important. All you have to do is change your nucleophile. Or in the case of this ring right here, you can be very selective. 2 bromines, 1 bromine on a primary, 1 bromine on a tertiary. We can even get a bromine on the secondary if we try really hard. But don't know how on this slide, but we can figure it out. All right, so the other thing about radicals is that chain polymerization. Okay, remember during the propagation step, you're adding across a double bond, creating another radical. And so that radical is going to be created right here where it's most stable, meaning that this is going to be the new bond every single time. And every single time it's going to create a radical that's going to attack this side. So it's a head to tail, head to tail. And it's a very regular system and it's very fast. It will go there. But that's not the only way we can make polymers. We can also do it with carbocations and carbanions. So let's talk about the shape of a carbocation, right? It's sp2 hybridized with an MPP orbital. Okay, so that's going to generate something that wants electrons and it's going to get electrons from the double bond. In the case of our radical, it's sp2 hybridized with an unhybridized p with a single electron in there. And so that's going to want to react and get one of these electrons and then move and form a bond and then have another electron left over. But if we have an anion, and the only place we've actually looked at those carbanions are when we make nucleophiles from like the alkynes and alkenes and alkanes. If you have an anion on an alkane, that is actually sp3 hybridized, and you have 2 electrons in the hybridized orbital, and then 3 other bonds. So that's a subtlety. But so if we have electron donating groups here, we can stabilize a positive charge right there. If we have electron withdrawing groups, we can stabilize a negative charge right there. And it does the same thing. It just keeps creating a negative charge. So it's like it's propagating just like a radical reaction, but it's actually a nucleophilic or an electrophilic reaction. But in the process, it generates the negative charge or the positive charge over and over and over. Okay, so that's all I want to say about radicals. So we learned a lot about how to prepare alcohols, and then in chapter 11, we learned we can use some of those reactions also to make ethers, okay? So really all we're doing is changing the nucleophile. It's an SN2 reaction, or sometimes an SN1 reaction, but we're just changing the nucleophile. So in the case of making an alcohol, all we had to do was attack with a hydroxide. Boom, you have an alcohol. That's great. Nice SN2 reaction. If you have an alkoxide, you will make an ether. Same reaction, just different nucleophile. And so we're going to make an unsymmetrical ether. And in this case, we have 2 of the same size to make a symmetrical ether. Remember, that's the Williamson ether synthesis, using an alkoxide or using an alkoxide as a nucleophile. Okay, now it works best when you have your alkoxide attacking a primary alkyl halide because of sterics. So it's best to, if you had to choose between 2 different routes, you want to choose your primary alkyl halide. Okay, all right. And then ethers don't do much unless they're the epoxies, okay? We can use 2 equivalents of HBr or HI, and that will break the bond here, but then it's going to create an alcohol, OH plus RX. And then this reacts also with HI to do a substitution reaction. It protonates the alcohol and then it uses as a leaving group. So you actually end up with two equivalents of your alkyl halide and one equivalent of water because the water got kicked off as the neutral water. Okay, but the best reaction in the ethers is the epoxy reaction. But remember, there's two mechanisms. If you have a good nucleophile, it's going to substitute on the less substituted side, sterics. It wants to come to the less substituted. But if you have acid in the system, it's going to protonate your epoxy first, and you're actually going to get your substitution on your more substituted side. So you can direct which side you are going to get your sample on here. All this took was a little drop of acid with our methanol, and it's going to go to the more substituted side. No acid and just water at the end, or maybe acid at the end, it goes to the less substituted side. So we can have regioselectivity. So that's one of those things you can put down on your reaction table. Okay. So we also learned we can take alcohols and turn them into alkyl halides. So this is kind of a good thing. We've learned how to mount alkyl halides from hydrocarbons using radicals. We can make alkyl halides from any alcohol. We can make alcohols from alkenes, and we can make alcohols from alkyl halides. So we can actually go completely in a circle of all the reactions now, okay? So of course, HBr and HI work really well, but HCl, especially with primaries, does not work well. We have to continue on our theme of making oxygen a better leaving group. And so we make it a zinc oxygen bond, which makes it a better leaving group, okay? On these cases here, we're making phosphorus oxygen bonds, which makes the oxygen a better leaving group. And in our last reagent, thionyl chloride, we're making a sulfonyl ester, which makes it a better leaving group. So we're doing that better leaving group trick on almost all of these. Okay, so we have two ways to make epoxies. We have one with a per acid, and the most common of those is metachloroperbenzoic acid. ClOOH. Cl. The other one, any other benzoic acid would work, but that's benzoic per acid would work. But any per acid will work to make this epoxy from an alkene. So it's just going to camp out on top of that alkene and make that double bond. But the other way we can do it is if we already had an alkene and we did a halohydrin reaction, so we have an halogen and an oxygen on adjacent, we're going to deprotonate that oxygen on the alcohol, and it's going to act as a nucleophile. Now, it's a lot of strain, but it has a lot of opportunity to close that ring because it's got everything it needs to close that ring, and it's just going to vibrate around until it actually closes the ring. And that's how we can create epoxy through an intramolecular SN2 reaction. Okay, so that's the reactions part. And now I'm going to do a summary of the spectroscopy. Okay, going all the way back to chapter 2. The most important slide in chapter 2 is know your zones. Okay, know that your light atoms are up above 25, and then triple bonds, double bonds, and then your single bonds. Look for those types of bonds in the functional groups. These doesn't tell you exactly functional groups. Well, cyano does, and sometimes carbonyl will, but there's other things here, right? And don't forget that our hydrogens shift around depending on what they're bonded to. Our oxygen is big and broad. Actually, we have two kinds of oxygen, right? We have alcohol, which is big and broad above 3,000. Then we have alcohol that is big and broad below, on the shouldering on the 3,000. It covers the whole thing. And of course, we have nitrogen. We can tell how many hydrogens are on that nitrogen by how many peaks are in that place. 2 peaks, 2 hydrogens. 1 peak, 1 hydrogen. No peaks, no hydrogen. Okay. And in NMR, we had 2 things to remember. In our proton NMR, we have 4 things to look for. Number of signals. the intensity or integration of signals, the position or shift, and the spin splitting. Now, make sure you look at the spin splitting patterns that were given in the, being able to recognize them quickly is going to help you. In carbon NMR, all we have to do is worry about our shifts and our number of carbons. So we have, it's a little bit easier, okay? And those values, note, they come in zones, right? Our hydrogens bonded to carbons come in this zone. Our hydrogens adjacent to oxygens, chlorines and nitrogens are here. Then we have our hydrogens on our OH and our nitrogen here. Then our alkenes, then our phenols, then our benzenes, and then our aldehydes and carboxylic acids are really high. Okay? So they follow this zone, they march all the way down. Now, in carbon NMR, we have the same zones. They just have bigger numbers. So we have just the carbons on things with oxygen, nitrogen, bromine, and chlorine are on that same region, followed by our acetylene. This is the kind of a weird one out here, but the alkenes and benzene rings overlap. Then this zone right here is carbonyls with an electronegative atom on it. And then the higher zone is for the carbonyls without an electronegative atom on it. Okay. And we don't have splitting, but occasionally it will be said where we have the doublet here is telling us that we have one hydrogen on it. The triplet here is telling that it coupled to that hydrogen. We didn't actually use this in class, but it is, and then this one is a quartet because it has 3 hydrogens on it. It's a weird experiment, but it's difficult and almost never used. Oh, carbon NMR is, yeah, doesn't integrate. But in hydrogen, we have to remember our N+1 rule. 2, 3 or fewer bonds. But there's also a caveat there. It doesn't split through oxygen or nitrogen. So it doesn't split through oxygen or nitrogen. So make sure you don't count those in your N number for the number of splits. The other cool thing is if you have an alcohol in your system and you want to make sure that peaks your alcohol, you can actually add deuterium oxide, and that'll take the hydrogen off the alcohol and replace it with deuterium, and it goes away. So you can prove exactly to everybody that that's your alcohol peak because it's the only one that it'll exchange at room temperature. All right, any questions on NMR? So with all of that and the exercise we did in class, I think you should have a good chance at getting them right on the exam. Okay. Then the last thing is mass spec. We only have 4 things in mass spec, which is the molecular ion peak. But remember, it's the big one, not the 1.1% one. It's the M+1. That's the isotope peak. And then we have the base peak, which is the tallest peak. That's our most stable fragment. Then we have our relative abundance of the different fragments, and then the fragmentation pattern. Is it breaking off? 14, 14, 14, 14. Okay. But we also have 3 advantages in here as well. Number 1, the nitrogen rule. If you have an odd molecular weight, it probably has an odd number of nitrogens in it. Okay. Then we have the 2 big isotope peaks, which are the bromine, which is 50-50, 1-to-1, almost, and then the chlorine, which is 3-to-1. So you can identify nitrogen, bromine, and chlorine in your mass spectra just for looking for those 3 things. Remember, these are M+2 peaks, M+2 peaks. It's 79, 81, and 35 and 37. It got cut off there. There we go. All right, any questions on what to study for on the exam? Now, this was, again, all the ones for the final exam, and of course, 8 through 11 for the one on Monday, May 2nd. Okay. And our finals on May 9th, not June, May. Okay, so that is all of the review on there. And I have prepared our last exercise for the year. Now, this should pull it all together. This should be, you should be recognizing these reagents. You should be trying to guess at these reagents. And if you're not, you need to go study a little harder because it's going to be important. Look at your reaction tables. When you go to the second half of this class, you're going to have to remember a lot of these reactions because they're going to be used in multi-step synthesis. So that's what I'm going to harp on a little bit right now. And then we're going to do a couple other examples. So if you're at home, you can go and download this off of Canvas. So let's talk about retrosynthetic strategies. Holy cow, what's that functional group? Right, we learned it in chapter 2, and we learned how to make it in chapter 6. We learned how to make it in chapter 6. It's an SN2 reaction using nitrogen as a nucleophile. All right, so let's see. That means we need to, if we know how to make that with a nucleophilic reaction, we have to have a leading group. So how are we going to get a leading group on there? It's an alkane. I think, yeah, radical is the only way we can get on there. So we're going to back that up to give us something with a leading group on here. So let's put bromine or chlorine. And we know how to make that, right? We're just going to add bromine or chlorine and peroxides, right? So then the next thing we'd have to do is attack it with a nucleophile. And that'd be 3 dot here. Why do I have ammonia as the nucleophile and not the anion, the amide? It's a weaker base, right? This is going to act as a strong base, and you're going to end up eliminating and forming your alkene. So we're going to use the weaker nucleophile, the weaker base, but it's still a decent nucleophile. We're going to use these lone pairs to do our substitution reaction and get to our amine. Okay, so we've talked our way through the backwards side of it. So now let's draw it for real. Okay, and we know what our reagents are going to be. So let's start with our cyclohexane. Here, we're going to do, let's do bromine because it's more selective, and peroxides. That's going to give us this, Br, which is actually even a better leaving group, so we don't have to heat it as much. And then I'm going to put it in a polar aprotic solvent. Sometimes there's going to be a solvent stated in there, and that can tell you, ooh, polar aprotic, is it going to do this? If it's a polar protic, is it going to do that? So you might get some help from there. And these are not very pretty cyclohexane. Let me try again. And then it autocorrects. Yeah. And then, okay, but there's going to be 2 there actually. When it first forms, it actually, because we're attacking with a neutral nucleophile, it's going to give us a charged species. NH, H, H plus. And then either, then another equivalent of ammonia can act as the base and deprotonate it, giving us our final product. Remember, when you get attacked, when you have an SN2 reaction with a neutral nucleophile, you end up with a positively charged product that you probably need to transfer a hydrogen off of, because there's only 5 things that happen in a reaction. Add a proton, take a proton away, attack by a nucleophile, rearrange, or break into a small fragment. You know, so try all of them if you don't know which one it's going to do. But when you have a positive charge, you're probably going to lose a proton. Okay, questions on that? So you see the strategy, right? To trying to do what you know and then take it a little bit further. Okay, so this one's a little more complicated. We're going to make a Tetrabromo compound. So I guess we're going to do a whole bunch of halogenation, right? Well, no, we're only allowed to start with acetylene here. Uh-oh, we got to do the counting, carbon counting thing now, right? Because we have too many. So we have 1, 2, 3, 4, 5, 6. Okay, so that means we need to add acetylene. We need to add 3 of these somehow. to our system. Okay, so I think the one way we can get to a Tetrabromo compound would be to have an acetylene in the middle there. It's going to give us the right number of carbons, and it's going to give us a place to do, with this would just be bromine and in dark, right? Just add it across there. Okay, well, to get to there, we'd have to actually maybe have acetylene, and we react it with an alkyl halide to get to the two bonds here. We'll do one side first and then the other side second. And then that gets it to a symmetrical internal alkyne. But how are we going to get to there? Well, okay, well, we have acetylene, so we can add HBr, and that's one equivalent, and that'll get us to here. And then we can just do catalytic hydrogenation, and that'll get us to our primary alkyl halide. All right, so now let's put it all together. We're going to go from beginning to end, and we're going to start on this side with acetylene. And I'm going to do one down with HBr, dark. And that's going to give us this. And then this is hydrogen with palladium to give us our alkyl halide here. Then we're going to take this with acetylene, one equivalent, acetylene, I'm going to put the hydrogens on here, one equivalent of sodium amide, and that's going to deprotonate it, and then that's going to give us this product here. And then we do that same thing again, one equivalent of this plus one equivalent of sodium amide gives us our triple bond in the middle of our species. And then all we have to do is two equivalents of bromine without peroxides. So we did every trick on that retrosynthetic thing. We counted the carbons, we backed up, we actually even made our alkyl halide from acetylene. Okay, so there's a lot of those on the homework for chapter 11. And I'm recording the chapters 10 and 11 homeworks tomorrow, so I'll have them uploaded hopefully tomorrow. Okay, so let's change gears a little bit and play fill in the blank. I wanted to do this as a retrosynthesis, but then I went from a 5-membered ring to a 6-membered ring, and I didn't want anybody to freak out and run screaming from the room, pulling their hair out, saying, "I'll never make it," because we will. So, but all we have to do is fill in the reagents. Okay. So, what reagents do we have to go from an alcohol to an alkyl chloride? Okay, HCl, but what do you have to add to it? This is the one you have to add zinc chloride. It doesn't work without the zinc chloride. Or SOCl2 or PCl5. Any of those can make that compound. And then we want to make sure that we got to dehydrohalogenate to get our alkene. So what we want to do is we're going to use a big base, T-butoxide. Why? Right. If we had methoxy, that's a primary alkyl halide. Okay. Methoxide and ethoxide are both good nucleophiles, but they're also strong bases. If we don't use T-butoxide, we could get a mixture of E2 and SN2 products. So we're going to use the T-butoxide and T-butyl alcohol to make sure we get it. And then what are we doing here? What reagent is going to do that? So what has to happen to do that ring expansion? Got to form a carbocation. Remember, we can have a secondary carbocation. We'll rearrange if it can go to a tertiary carbocation through a 1,2 hydride shift, through a methyl shift, or through a ring expansion. Okay, that means we had to have a carbocation here. So, and then bromine came and attacked it. So I guess we'd have to add a hydrogen here to generate a carbocation there. Then this is going to move around here. So we had to put a hydrogen on there to get our carbocation. And we need bromine at the end. So HBr. So it's just HBr. No peroxide in the dark. So, and then what that's going to do, of course, is it's going to give us our ring expansion, and then our carbocation gets reacted with the bromine. Okay. See how you can identify different reagents to fill in what the starting materials and products. All right, let's do one more of those. Actually, two more of those. Okay. So this seems like a silly transformation. I started with a terminal alkene, and I turned it into a much more stable transalkene, and it's an internal alkene. So I just needed it more stable, and I didn't have it. So what are we going to do? We have bromine. It's going to be on that secondary carbon. So I think we're just going to add HBr again. HBr. It's not going to move. There's no tertiary possible, so it's going to stay there. And then what we can do here is, well, now we can probably use ethoxide because we have a secondary. Okay. And so it is less likely to undergo an SN2 reaction, even though it's a good nucleophile, it's a better base. And therefore we can use the ethanol with ethoxide and give us. See how we were choosing our base specifically because we had a primary, which would give us the wrong product. It would give us a mixture. The secondary, remember, look back at your table, only does E2. In a hindered primary or a secondary or a tertiary, it does the E2. All right. So now we have something really crazy on the bottom here. Okay, this is one of those nucleophiles we haven't played with very much, but it's in the book, and it's also was on, I think, one of the quizzes. So, so let's see, to make this right here, so that means we just had to ring open this by attacking it with a good nucleophile. So CH3 sulfur anion. That's one of our nucleophiles. So it can make that thioether. That's one of the functional groups we made in chapter 6. Okay, so how do we make that epoxy? Well, we could do a halohydrin reaction and then do a Williamson ether synthesis, or we can just use metachloroperbenzoic acid to make it dry. So see how being able to recognize the reagent, you see what's changed. Okay, you look for the change, the functional group change, and then you think about the reagent that made that change. All right, so now the last one. Dun, dun, dun. And I actually have the reagent wrong on the answer, by the way. I need to go switch it. I wrote the wrong reagent. I was rushing. But so anyway, so gosh, let's see, we got to do that. All right, so we already have an alkene and we have carboxylic acids. So we know we're going to do a cleavage reaction, but let's make sure we didn't lose anything. We have 1, 2, 3, 4, 5, 6 carbons in the long chain, but we're adding an ether to it. Okay. So we probably can't add the ether to the carboxylic acid while it's there because it's going to react. You'll learn next semester, they'll react with the carboxylic acid first. So we need to put that ether on before we clip the ring. Okay, so that means we have to back it up such that that ether has to be on there before we clip the ring, and OME. Now, why did I put it there? Well, when we clip this ring, this is going to turn into one of the carboxylic acids, and this is going to turn into the other one. So that means it has to be in that location before we clip it. Okay, do we see why that is? That's where we're going to break it. What would we break the double bond with anyway? Permanganate hot, because we're making carboxylic acids. If we were going to stop at the aldehydes, we could do it with the ozone and dimethyl sulfide. We can make aldehydes too. So, but this was carboxylic acid, so the right answer is permanganate. So to back up from there, we have to do some kind of nucleophilic attack. So we're going to do bromine here, and we have our double bond. Okay, doesn't look as clear as it could. Double bond right here, right here. So do we have a reaction where we could put a bromine next to an alkene? We have a radical reaction where we use NBS and peroxides, and we have formed the allylic radical, and then the allylic radical is stable enough to have the bromine come down, and we still have our double bond. We didn't destroy our double bond. We just did a substitution reaction. So that means we can back that up to NBS. Let's see, I think there's, H nu or heat or peroxides, ROOR. And that takes us to our allowable starting material here. So let's put it all together. Okay, we're going to start on this side right here with our alkene. We're going to do NBS with, let's just do peroxides. They're fun. Which is going to give us our allylic substitution, bromine. And then we're going to do methoxide. Ooh, should we use methoxide here? Well, it's going to give us a little bit of side product because it can act as a base. It's a good nucleophile, but it can act as a base. So it might give us some E2 stuff here, but it's still going to give us some of that. So it's maybe not the best way to do it, but we can make it happen and get our OME. And then let me go ahead and clear these out. And then our last reagent is, not kind of arrow. We're actually doing a reaction. Potassium permanganate, usually with a base in water. Okay, so these are the reasons that I'm wanting you to learn your reactions both ways and learn the reagent too. Okay, so except for, let's see, which one? No, this one's wrong. Yeah, we need to do NBS. So, but the answers are on the last slide. All right, questions on that. So that's the activity I had planned for you today. And if you have any questions, go ahead and stay behind and ask. If not, go ahead and study well. Think about how fast you were able to answer the questions to this, or if you couldn't answer them, then you want to study that, before Monday's exam. Okay. All right. Any questions from home? Okay. Well, I'm going to go ahead and stop sharing and stop recording.